Large language models are becoming more and more powerful, but the computational cost of processing long text is also increasing dramatically. Today, we'll share a new research from DeepSeek AI. They propose a method called native sparse attention while maintaining model performance. It increases the processing speed of 64K length sequences by at least 6 times. This video will provide a detailed interpretation of the paper published on AR-Zivtitled native sparse attention, hardware-aligned and natively trainable sparse attention. As the application scenarios of large language models continue to expand, the need to process long texts is becoming increasingly important. Let's take a look at a few specific application scenarios. In code generation tasks, the model needs to understand the context of the entire codebase. In multi-turn conversations, the model must remember previous dialogue history. In complex reasoning tasks, the model needs to process a large amount of background information. These scenarios place higher demands on the model's ability to handle long sequences. However, there is a key technical challenge here. The standard attention mechanism encounters computational bottlenecks when processing long sequences, specifically when dealing with sequences of length 64K, approximately 64,000. The attention computation accounts for 70 to 80% of the overall inference latency. This means that most of the model's time is spent computing attention. To address this issue, the research community has proposed various sparse attention methods. For example, the KV cache, key value cache, eviction mechanism, which saves memory by dynamically deleting unimportant historical information. Another example is the chunk selection strategy, which divides the input sequence into multiple chunks and only focuses on important chunks for computation. However, these existing methods often face two main challenges. The first challenge is the gap between practical results and theoretical expectations. Although theoretical calculations can significantly reduce computational load due to irregular computation patterns and random memory access, no corresponding speed improvement is achieved on actual hardware. The second challenge is the limitation of the methods, as most approaches focus on optimizing the inference phase without considering how to introduce sparsity during the training phase, which prevents the model from adapting to sparse computation patterns during training. The innovation of the NSA method lies in solving both problems simultaneously. Let's take a closer look at its algorithm design. The NSA adopted a hierarchical sparse strategy. First is the token compression mechanism, which observes token blocks in the input sequence and compresses consecutive tokens with similar or related information into a more compact representation. This not only reduces the number of tokens that need to be processed, but also retains the main features of the original information. Next is the token selection strategy. Among the compressed tokens, NSA will use importance Geresto, select the most critical token blocks for precise computation. This selection is not random, but is based on the semantic importance of the tokens, their positional information, and their relevance to the query. This ensures that the model can focus computational resources on the most valuable information. The third key strategy is the sliding window mechanism. To avoid missing important information, NSA maintains a local sliding window, ensuring that each token can interact with its nearby context. This design maintains text coherence while greatly reducing unnecessary attention calculations between distant tokens. In terms of engineering implementation, NSA has conducted a series of deep optimizations for modern hardware. First is the balance of computational density. NSA adopts a fixed-size block strategy, dividing the attention computation into uniformly sized computational units. This regular computational pattern is very suitable for the parallel processing characteristics of GPUs, allowing for full utilization of computational resources and improving GPU utilization. Next is memory access optimization. Traditional sparse attention often generates a large amount of random memory access, which leads to low cache hit rates. NSA, through carefully designed data layouts and access patterns, ensures that related data is stored as closely as possible. This continuous memory access pattern can significantly improve cache hit rates and reduce memory latency. Finally, the optimization of training support. NSA has designed an efficient backpropagation algorithm, allowing sparse attention to be introduced during the training phase. This algorithm not only ensures the accuracy of gradient computation, but also reduces memory usage by reusing the computation results from the forward pass. This end-to-end training support enables the model to better adapt to the sparse computation mode. Let's take a detailed look at the experimental results of NSA. First, in terms of performance, researchers conducted tests in multiple scenarios, including general benchmarks, long text tasks, and reasoning evaluations. The results show that NSA not only did not lose model performance, but even performed better than the full attention model on certain tasks. In terms of speed improvement, the experimental data is exciting. When processing sequences of 64K, approximately 64,000, in length, using NSA's model achieved an 11.6x improvement in decoding speed at the same time during the model training process. The speed of forward propagation and backward propagation improved by 9.0x and 6.0x, respectively. This means that NSA can significantly improve the operational efficiency of the model, whether in training or inference stages. Another noteworthy advantage is the training friendliness of NSA. Unlike some other methods that require modifications based on pre-trained models, NSA supports end-to-end training from scratch. This design allows the model to fully adapt to the computational pattern of sparse attention during the training phase, thereby achieving better performance in practical applications. Of course, the NSA approach also has some limitations that need to be noted. First, due to the different architectural characteristics of different hardware platforms, NSA needs to be specifically optimized and adjusted for each hardware platform, which increases the deployment workload. Secondly, the token compression and selection strategies in NSA involve multiple key parameters. These parameters need to be carefully tuned according to specific application scenarios. Otherwise, they may affect model performance. In addition, when processing shorter sequences, NSA's pre-processing steps may actually bring some computational overhead, making the overall performance not as good as standard attention mechanisms. This means that when choosing whether to use NSA, it needs to be weighed against the actual application scenario and sequence length. Overall, NSA provides a practical solution for large language models to process long text that is not only theoretically elegant, but also well thought out in terms of engineering implementation. It is a rare work that has both academic and engineering value. The development of this technology may help large language models to function in more long text scenarios, such as processing entire code bases, analyzing lengthy documents, and conducting multi-round in-depth conversations. Of course, its actual effectiveness still requires more practical testing. That's all for this video. If you found it helpful, please like and subscribe. If you're interested in the related content, you can also check out the original paper for more technical details. Thanks for watching.